Hello everyone. Today we are going to learn how to construct orbital diagrams. Electrons are housed in orbitals, which are three-dimensional regions of space where they are most likely to appear. There are many different kinds of orbitals, and each one has its own unique shape. For example, s orbitals usually look like spheres. Different types of orbitals have different number of orbitals in each set that arrange themselves around each other in three-dimensional space. A set refers to all those who have the same principal energy level number. In electron configuration, this would be the number that comes before the type of orbital. In an S, there is only one available orbital in the set. For P, there are three, one along each of the three-dimensional axes X, Y, and Z. For D orbitals, there are 5 in the set, and for F, there are 7 in the set. You may notice a pattern. It is always odd numbers. So for example, if G orbitals were found to exist, G would be predicted to have 9. Each orbital can hold up to 2 electrons in it. One electron will be spin up, usually represented by an arrow pointed upwards in an orbital diagram, and the other is spin down, usually represented by a downwards arrow in an orbital diagram. This idea is known as the Pauli exclusion principle, the idea that electrons must spin in opposite directions if they are in the same orbital. In fact, there are 3 primary rules one must consider when constructing an orbital diagram. The first of these is the Pauli exclusion principle. The electrons who are in the same orbital have opposite spins, which is generally represented by opposite directions on arrows. Another, which is also followed for electron configurations, is the off-bow principle. Electrons fill the lowest available energy levels first before continuing to higher energy levels. There's also a third rule in effect here, known as Hund's rule. For Hund's rule, electrons that are going into a set of orbitals of equal energy first go into the orbitals alone before they pair up. For example, a set of p orbitals contains 3 orbitals. If you had 3 electrons going into those p orbitals, they would go into one each into each of those 3, rather than pair up, because electrons don't really want to be near each other because they have similar charges. So what do orbital diagrams look like? There are many different ways to write orbital diagrams. Sometimes the orbitals are represented by boxes, other times by lines. Sometimes they are written horizontally next to each other, like shown on the far left. Other times they are shown one on top of each other, like in the middle, and sometimes they are stacked in a sort of zigzag way to represent the idea of principal energy level splitting, as shown here on the right. What we will do in this class looks more like a combination of the one in the middle, where they are stacked on top of each other, with the boxes from the other 2. So let us practice and construct an orbital diagram for carbon. Carbon has 6 electrons. And so because of this, we're only going to need a few orbitals at most. We really should only need 3. However, since in order to gain a third orbital, I need the p, I will draw the boxes for all 3 of the p orbitals in case I need to follow Hund's rule or anything other rule. So currently, we have boxes to represent the 1s orbital, the 2s orbital, and the 2p orbital drawn and ready for arrows to be placed in. Let us go down to the 1s orbital and place 2 arrows, one pointing up, one pointing down, to represent the first 2 electrons for carbon. You'll notice I have single-headed arrows here, but double-headed arrows work equally as well. Then, into the 2s orbital, we will place 2 more. We now have 4 of the 6 electrons placed. There are still 2 more remaining, which will go into the p orbital. Now that we have a set of orbitals, we need to be careful. Hund's rule must be obeyed. Since we have 2, they will go into separate orbitals rather than be paired together. The completed orbital diagram for carbon is shown here. The 1s and 2s orbitals are filled, and the remaining 2 in the 2p are each in their own separate orbital. Let us continue practicing how to construct orbital diagrams by doing a larger atom, chromium. Since chromium is number 24, I will need at least 12 orbitals in my diagram in order to construct chromium. In order to get up to 12, I will have to go all the way up to the 3d orbitals and actually have a little bit over 12. This implies that Hund's rule might be in effect, and or there may be some orbitals that are empty, like there was an empty one for carbon. So let's start by filling the lowest available and working our way up towards that final one. So we have the 1s, 2s, 2p, 3s, 3p, and 4s orbitals all filled. We are now currently at 20 electrons. There are 4 more that need to be placed, and they will be placed into the 3d. How will they place themselves into the 3d? In order to follow Hund's rule, the 4 electrons must be placed into separate orbitals as shown here. The completed orbital diagram for chromium is shown on the right of this slide.